Physical disks are inherently slow. A mechanical hard drive maxes out around a few hundred megabytes a second. Yet, stateful systems like Kafka process millions of messages per second, writing all of it directly to disk. This split-screen chart illustrates the physical constraints of disk hardware. On the left, random writes max out around a microscopic 100 kilobytes per second. On the right, sequential writes on the exact same disk soar to 600 megabytes per second. Standard relational databases frequently rely on random writes to update records in place. This forces the disk head to physically seek across the platter, causing fragmentation and immense latency. Kafka sidesteps this entirely by strictly enforcing sequential writes. Every single message is appended to the end of a file. By removing the need for the disk head to seek, Kafka hits that 600 megabyte per second hardware ceiling. Kafka derives its throughput from mechanical sympathy, a design philosophy that aligns software architecture with the physical constraints of the hardware. But disk speed is only half the equation. Data-heavy applications face a second major bottleneck: the runtime environment itself, specifically the Java virtual machine. Traditional message brokers operate by pulling data from the physical disk up into JVM user space memory. The application processes or routes the payload, and then pushes it back down to the network layer to reach the consumer. This path requires multiple data copies in memory and expensive CPU context switches between the operating system kernel and the JVM. Kafka achieves extreme throughput by removing the JVM from the core I/O path entirely. It delegates the heavy lifting directly to the Linux kernel. To see how this works in practice, we have to examine three distinct layers: the sequential log structure on disk, the zero-copy read path, and the OS-managed write path. Kafka stores data on the broker's local disk, separated into distinct topic partition directories. To maintain high throughput, the broker operates under a strict stateless design constraint. Messages are only ever appended to the end of a file. They are never modified in place, and they are never individually deleted. In this myTopic1 directory, a single .log file fills sequentially. When it hits exactly 1 gigabyte, it is capped, and a new block spawns. These segments are named by the offset of their first message, mapping an exact chronological sequence. Once capped, the older segments become immutable historical logs. At any given moment, only the single newest segment, the active segment, receives new incoming writes. This rigid 1 gigabyte append-only structure ensures that the operating system receives long, continuous streams of data. It forces pure sequential I/O and prevents file fragmentation at the hardware level. This creates a retrieval problem. When a consumer requests a specific message offset, scanning through a massive 1 gigabyte binary file from the beginning would consume excessive CPU cycles. Kafka pairs each segment with an index. In this split view, the left terminal maps a logical offset of 50 to physical byte position 4098 in the .log binary. Using a sparse index, it leaves a 4 kilobyte gap before the next connection. By default, the broker writes a new index entry strictly for every 4 kilobytes of data volume it processes, skipping the messages in between. When a request arrives, Kafka performs a rapid binary search on the small index file to find the nearest mapped physical position. From there, it only has to execute a very short sequential scan through the .log file to locate the exact message. Sparse indexing keeps the memory footprint exceptionally small. The index files are compact enough to be loaded directly into RAM using memory-mapped files, balancing rapid retrieval with low memory consumption. With the data physically located, the broker now has to send it over the network to the consumer. In a traditional I/O flowchart, a data packet moves from disk to kernel buffer, crosses up to JVM user space, then back down to the kernel socket, and out the network card. These kernel JVM boundary crossings flash red, triggering 4 expensive CPU context switches. Because a Kafka broker stores and routes binary data without processing or mutating the payload, it circumvents this path using the sendFile system call. The flowchart updates. Bypassing the JVM entirely, a direct arrow routes data from the kernel cache straight to the network socket via direct memory access. Kafka pairs this with mmap for the smaller index files, allowing the operating system to manage index caching efficiently in the background without user space intervention. Zero copy eliminates the CPU bottleneck on the read path.
A Kafka buffer can entirely saturate its network bandwidth, streaming gigabytes of data out to consumers without causing a spike in JVM memory usage. The write path operates under a similar philosophy, defying a common professional misconception, the assumption that a highly reliable database must synchronously execute an fsync command to write every single incoming message to the physical platter immediately. Forcing a hardware-level fsync system call for every message incurs a massive latency penalty. Doing so would instantly destroy Kafka's throughput. In Kafka's actual write architecture, incoming data is written directly into the Linux page cache in RAM. The moment data hits the cache, a green acknowledgement signal bounces back to the producer, while the actual data blocks slowly drip down into the physical disk layer below. Kafka explicitly delegates the physical flushing of this data to the operating system. It relies on the Linux kernel's background processes to batch and write the data to disk efficiently. Writing to memory before disk introduces a clear risk. A sudden power loss on that specific node will result in the loss of unflushed pages in the cache. Kafka mitigates this hardware-level risk at the system level. It relies on strict cluster replication across multiple separate nodes to ensure data durability, deliberately trading single-node synchronous hardware writes for extreme network throughput. Even internal consumer state is handled this way. Tracking which messages have been read was migrated away from external systems like Zookeeper into a native internal Kafka topic called _consumer offsets. By treating state management as just another append-only data stream, Kafka leverages its own high-speed page cache architecture to manage consumer progress without relying on slow external bottlenecks. Tracing a message from ingestion to consumption reveals a highly optimized data lifecycle. Looking at this macro view of the broker architecture, the data flows smoothly. An append-only write hits the page cache, updates a tiny index map, and then shoots directly out the network card via DMA, never once touching the JVM box in the center. Under the hood, Kafka functions as an API wrapped tightly around Linux file system optimizations. By aligning its data structures with the operating system rather than fighting it, Kafka turns cheap, slow-spinning disks into high-speed network buffers. When evaluating high-throughput architecture, the primary goal isn't necessarily writing faster application code. True performance at scale is achieved by designing data structures that allow the operating system to do the heavy lifting for you.